Hey, Honors Physics, this is Mr. Hausman. If you're here, you're probably interested in finding out a little bit more about what's going to be on the projectile concept quiz. And we're going to do a quick and comprehensive review. But I also know that some people are just here to check their answers to some of the practice problems that are in the packet. So I'm going to jump to that right now. And then I wanted to go back to this page and talk about kind of the key ideas. So if you're still on board, that's great. But if you want to maybe skip this part because you already know it, that's fine. So what do all of these have in common, right? All projectiles are moving. They move in two dimensions. They move in the x direction and they move in the y direction. Okay, they can be up or down. The result of that is that they have curved paths, and the better way to describe that is a parabolic shape. And specifically, it's a trajectory. So parabolic trajectories are the shape. So we've got a baseball that's got a curved path. We have a human cannonball that's got a curved path, shooting a basket. Of course, cannonballs, bullets, things like that. And don't forget about orbits. Orbits are a curved path that never hits the ground, but they are still considered a projectile because they're in air or space. And their path can be described with a parabola. So those are some of the key requirements. Now, what are some assumptions? One assumption is that the only force or the only significant force is gravity. But of course, in real life, there is friction or drag, but from a quantitative standpoint, we're not handling that, but we do know that drag is air resistance, and it slows down both your Vx and your Vy initial. So it gets quite complicated. You're reducing your horizontal, and it really does throw off many of the equations we've been using. Okay, I think those are the key ideas that we looked at. Maybe some examples or non-examples of projectiles, or are anything with, we'll put a big circle around them, anything with wings, anything with engines, anything with propellers, and all of those are non-examples because they create lift, or they create thrust, or they create other forces. Go back of kind of review. So this page was earlier in our lessons, just in case a quick review. So analysis of a horizontally launched projectile, actually it's true for any projectile, is that in the horizontal direction there is no sideways force, right? There's no forces in the horizontal direction. There is, yes, a pull of gravity, and it's a pull downward in the vertical direction. There is a force. Therefore, there is an acceleration. Forces always cause accelerations. Forces don't cause movement. Forces cause accelerations. Since horizontal had no force, it has no acceleration. Therefore, if you have no acceleration, you would have a constant Vx, but you would have a changing, always changing velocity. And most of us are really good at these tables. We won't be doing problem solving, but you kind of know how to read those variables, okay? So there's in the way, last review, the last part of the conceptual quiz that you're going to encounter is to make sure you can really understand that Vx is actually really is constant. You can say it, you can answer questions, but do you know that what that implies is that the horizontal component basically stays fixed the entire way through the flight, and the vertical component, right, starts off at 0, and it's doing its own independent thing, right? It's determined by gravity, which is about -10 meters per second every 1 second. So that means it's becoming more negative by -10 every second. And when we first started this, we also made the conclusion that you can find the V final, or the resultant velocity. Of course, you can do that by taking Vx, squaring it, Vy final, squaring it, and that's going to be the V resultant squared. And the angle, inverse tan of Vy final over Vx would get you your angle. So some of the pages that I suggested that you look at are 24, 25, 26, I think in 27, 4 pages. And we started a few of these in class. But here's the big picture. Let's make sure we've got all the answers. Okay. So the first question that's on page number 24 is all about the V naught. What happens to the flight, the variables, the dependent variables, if the V naught is the independent variable, is the variable you change? So we have a scenario where we have a 30, a 40, and a 50 meter per second. And you can see that each one has a different trajectory. The 30 meters per second has the shortest, the 40 a little further out, and the 50. So we did this in class, but just a quick recap. We have, let's see if we have a good color to work with here. So the V naught would change the Vy initial by increasing it. The delta Y would stay the same because the delta Y is the height from beginning to end, and there is 0 for all 3 of those. The time in the air would also increase, similar to the Vy initial. The Vx would also increase. The horizontal displacement, I think that's the easiest to see. That's also increasing as you increase the V naught. So if you want to explore that, the reason why the 2 components increase is because the 30 versus the 40 versus the 50, they would each have slightly larger and larger x and y components. Those are the velocities components. So there's a good start. The delta y is the same because they all start and end at the same height. And the time would increase because the Vy initial would be larger and larger, and that would mean it takes more time to get to the top because gravity can only slow it down at a certain rate, and therefore it would take more time to get back down. So the larger the Vy initial, the more time to get up, the more time to get down, so a total overall increase. The second question was more about the angle, right? Increase the angle, but keep the velocity fixed. And that's a little bit of a trickier question. So if you increase the angle from 0 to 15 to 45 to 75, those are the 3 options. There's a kind of an interesting kind of paradox. The Vy initial starts off very small, right, at low angles, and then gets bigger and bigger. So that's a consistent increase. The delta y stays the same because they all land at ground level. The t gets to be larger and larger, and the Vx gets shorter and shorter. I think you can see that at 15 degrees, the x component is this long, and then it would be a little bit shorter right here, right? The 45 would only be this long, and for the 75, it would be this long. Let's change to a more typical pointer instead of the lightsaber. So long x component, short x component for 45, and the shortest yet for 75. So that's a decrease. The horizontal displacement is kind of the one that's not a trick, but you have to think about. As you go up from 15 to 45, it increases. From 0 degrees to 45 degrees, there's an increase. But then once you get past 45 to 90, so greater than 45 and up to 90, now the displacement is starting to decrease. So we've got a split answer. Next up, applying concepts. The soccer ball is kicked the 3 different pictures below. And the variables that we're going to be using, we're going to be ranking initial velocity. Who would have the largest initial velocity? Who would have the largest time of flight? Et cetera, et cetera. And that gets really challenging. So I see a soccer ball that for some manner is all getting to the same height. if they're getting to the same height, then their times of flight would all be the same, right? It would take the same amount of time to get up and the same amount of time to get back down. Interestingly, based on previous problems, that also means the y component for all of them is equal, right? If they have equal times, then they have equal y components. So then what seems to be the difference? Why would 3 go farther? And it's because this is the largest. We would have the largest, if we were to rank them, we would have the largest, and then 2 would have the second largest, and then 1. Okay, so they're all equal for initial velocity and time, but because 3 goes farther in the same amount of time, it must have a larger x component. Now, let's put those two together. If projectile 3 has the largest x component and the same y component, it's also going to have the largest hypotenuse, right? So if the x component is one factor and the vertical is basically locked in, the larger this gets, the larger your hypotenuse is going to get. So it's 3, 2, 1 again. And you can see that on the bottom of the page. Or, here we go. Now we have a projectile. This is a relative motion problem. We haven't gotten to this one. I'm going to still give you the answer and see if you want to play with this. Here are 5 asteroids on and a spaceship. They're all moving in the same direction away from Earth. So here's Earth. Let's make it the big blue marble. And they're moving away. So if they're moving away, gravity's pulling them back. List the asteroids that are moving toward the spaceship. Right now, let's see. Oh, this is because it's a relative motion problem. So here's the spaceship moving away from the Earth. It's going 600. So if A is positioned on the left side, so to speak, I don't know, maybe it's closer to Earth and the spaceship's farther away. This is the right side. If these two objects have the same velocity, will they ever get closer? Will they ever get farther away? So A is not moving toward the spaceship. It would be maintaining the same distance. B would get closer and closer because it has a velocity greater. C would also be moving closer and closer. D, on the other hand, would be moving farther away because essentially it's not keeping up with the spacecraft. It has a lower relative velocity. Okay, and then, maybe the answer should be up there for that, and we'll erase this one. And then the asteroid that's further out from the spacecraft, it is slower than the spacecraft. So in a weird way, while the asteroid may not be getting closer to the rocket because it's moving toward it, the spacecraft is going to be moving closer to the asteroid. So the distance here would get shorter and shorter if basically the spacecraft is kind of catching up. Okay, what's your reasoning? I think we kind of overheard these. So did we answer all of them? I guess we didn't answer A because it is actually maintaining the same distance. Okay, we did number, let's see, what is this? This is 4, this is 5 in class. The largest time in the air is determined by the height. So B and C are tied, right? They're both first place, and then second place would be the D because it's 30 meters off the ground, and then A. So it has nothing to do with the muzzle velocity or how fast you shoot it. The time in the air is determined totally by the height. Okay, let's get going. Now all the arrows shown were shot from the same height. Okay, we have to read this detail, and at the same angle. Though the arrows have the same size and shape, they're made of different materials, so they have different masses, and they have different speeds when they leave the bows. Okay, so the mass has no effect on the height or any of the flight parameters. So let's get that straight. The mass does affect maybe the initial velocity, because if you have the same string shooting the arrow, the heavier arrow won't go as fast. But the mass has no effect. Oops, I think that's a verb, effect, on the projectile, right? It has some effect on maybe the initial velocity, but once it's in the air, it has no effect on it. So disregard the mass. In terms of greatest height, okay, so who would have the largest y component? So if you want height, you need to get more time. And how do you get more time? You get it by having a larger VIY. So who would have the largest VIY? Well, that would be C, because this side of the vector triangle, that component, the y component, would be biggest if the hypotenuse or the v naught was 16, and then B, and then C, and then A and D would be tied for third place. Want some? Okay, let's keep going. All the cannons in the figure are identical, and they're aimed at the same 35 degrees. The cannonballs are all the same size and shape, but the masses of the cannonballs, as well as their speeds, leave the cannon are different. So we already talked about how mass has no effect. Right, on a projectile's flight. So what determines, they're all at the same angle, and but they are at different speeds. Rate the acceleration when they reach their highest point. So what acceleration is there for a projectile? Well, the only acceleration is g, and that's vertical, and that's negative 9.8 for all of these. So they're all the same, okay? So instead of writing out our explanation, you're just listening to the video. Let's go to the next one. Got a couple more to do. Two toy trucks roll off a table. The heights of the tables and the speeds and the masses are given. Okay, we ready for this? Mass, no effect. Okay, so the bigger the height, the more time, but the Vx in this case, right, is different. So will truck A be in the air for a longer time or shorter time as B? Okay, so if it comes to time, okay, and all they ask about time is who's got the larger height. So A, right, so A's time will be less than B's time. Why? Because height in the air, the amount of space it takes to fall, will determine how long gravity takes to pull you back down. And then one more, I have to kind of pick it up just to see it better. Two trucks roll off the ends of identical tables. The speeds and masses are given. Now the heights are the same, right? So we've already established mass is not a variable, but now height of A is equal to HB, so their heights are the same. Will A be in the air for a longer time, a shorter time, or the same time? I say the time for A is equal for the time to B, because the height determines the time in the air. Okay. Lastly, this one is more of a what kind of projectiles have we examined and kind of what parameters. So we started with horizontal launches, and that means the angle was 0, the Vx was constant, the Vy initial was 0, and the delta y was always negative, right? So we've got a negative delta y, we've got a positive delta x, and there was no vertical velocity, right? So you can't even really draw an initial velocity. 1 second later, or a fraction of a second later, you can put in, right, a horizontal and a vertical, and then when it lands, it has the largest yet. But there was a 0 Vy initial to begin with, okay? Then, right, so this was horizontal. All of these down below are angled projectiles. That means the theta was not 0. So we have a positive angle, we have a constant Vx, we have a Vy initial that's positive, and a delta y of 0, right? Delta y is 0 because it has gone up and come back down and lost all of its vertical displacement. So here's Romeo throwing a pebble at Juliet's window. In Romeo and Juliet, we have a positive angle because it's upward. We have a Vx that's constant. We have a Vy initial that's positive, and a delta y that's positive because the pebble has landed against the glass to wake her. Okay, here's a football punt, and this one's more realistic. So football players' feet, when they punt, are quite high. They elevate, they drive through the ball. Then it lands on the ground, assuming maybe no receiver catches the ball. We now have a positive theta. We have a Vx that's constant. We have a Vy initial that's positive, right? We can see that by sketching it in. And we have a delta y that's negative. We saw some of those. And depending on which problems you did in the problem set, we also saw negative angle problems. So this is being thrown at a downward angle, negative 30 degrees. We could have also called that a 330-degree angle for trigonometry purposes, but it's below the horizon, so it's a negative angle. The Vx is still constant. The Vy initial, that's now negative, right? So if you look carefully, that's a negative vector pointing downward, and the delta y is still negative. So I think that's the end of the pages that you might have been coming to check your answers.